A priority queue is an abstract data type. We call that in order to define an abstract data type, we need to specify which operations are performed on that data type and what these operations accomplish. But we do not specify how the data is structured and how those operations need to be performed. So a priority queue stores a collection of items where each item has a priority. We can perform three operations on this collection. The add operation adds an item with a priority. The get operation returns the item with the highest priority among all items. And the remove operation removes the item with highest priority. Let's trace a sequence of sample operations on a priority queue. The priority queue is represented by the circle on the right. Initially, the priority queue is empty. The items we insert are just numbers. The lower the number, the higher its priority. In other words, the lowest number in the priority queue has the highest priority. The first operation adds the value 7. Then we add the value 3. And then we add the value 5. The fourth operation is a get operation. Note that we do not specify which item we want to get. The item that will be retrieved is determined by the priorities of the items. The one with highest priority is retrieved and returned. In our case, 3 has the highest priority since it is the lowest value. Note that 3 is only returned but not removed. Now we perform a remove operation. Again, we do not specify the item that is removed. The value 3 will be removed since it is still the value with the highest priority. Finally, we perform one more remove operation. This time 5 has the highest priority and therefore 5 is removed. If you could follow so far, you should be able to answer the following question. If not, review the previous slides. Assume a priority queue stores numbers. Now the higher the number, the higher the priority in this case. We insert the numbers 10, 16 and 14 into the initially empty priority queue. And we insert these items in that order, first 10, then 16 and finally 14. After these three insert operations, we perform a remove operation. So the question is now, which item will be removed from the priority queue? Okay, here's the answer. 16 is removed since it is the highest number among 10, 16 and 14 and therefore has the highest priority. Note it does not matter in which order the elements have been inserted before. So the remove policy is very different from the remove policy of a queue. In spite of its name, the priority queue is not a queue. Now it's time to think about how to implement a priority queue. We are familiar with many data structures that could be applied, including linked lists, sorted linked lists, sorted arrays, binary search trees, and AVL trees. I've included the heap in this list, which you will learn about in the next video clip. Let's look at the time complexity of each operation of the priority queue if we use the corresponding data structure. As we usually do, the complexity is measured in the number of elements in the priority queue. If a linked list is used, we can add a new element at the head, for example. Then the add operation can be done in constant time. For the get operation, we need to find the element with highest priority first. Since it can be in any position, the entire linked list has to be traversed to find that element. Hence, the time complexity of the get operation is O of n. Similarly, we need to find the element with highest priority first for the remove operation, and then it needs to be removed from the linked list. This is also linear in the number of elements in the linked list. Maintaining a sorted list where the items are sorted by their priority is possibly an improvement. If the list is sorted from highest to lowest, then we can get and remove the element with highest priority in constant time, since the element with highest priority is at the head of the list. However, now the insert operation is linear, as we have to find the position where the new element is to be inserted, which takes O of n time. The time complexity for a sorted array is the same as for a sorted linked list, if we make sure the array is sorted from lowest to highest priority. The element at the end of the array is the one to be returned by the get operation, and similarly the last element is the one to be removed. Now for the insert operation, we can find the position where a new element is to be inserted in logarithmic time by using binary search. However, when the element is to be inserted into the array, all the elements to the right of the insert position need to be shifted by one position to the right, and therefore the overall time complexity of the insert operation is still linear. Remember that all operations on a binary search tree are linear in the worst case, so depending on the order in which elements are inserted, the performance might be much better in practice. We can use the priorities here again to compare the items in the priority queue. The add operation for priority queues corresponds then to the add operation in a binary search tree. The get operation boils down to the find maximum operation, and the remove operation removes the maximum element in the binary search tree. Each operation is linear. If we use AVL trees, then the time complexity of these operations is logarithmic, so the AVL tree option looks pretty good overall. Remember that the logarithm has a very slow growth rate, such that even for a very large number of elements in the tree, the time should be quite good. However, if the get operation is a frequently performed operation, as it is often the case, then a sorted list or array might be better. We will see another option, the heap, in the next video clip. The add and remove operation in a heap have logarithmic time each, and the get operation is even constant.